Hello, ET370. This is our Tuesday lecture. What we're going to cover today is an edge-triggered binary counterexample that builds off the last example from the previous lecture. And then we're going to talk about this idea called synthesis of logic. Synthesis is the opposite of analysis, where analysis you're kind of analyzing a system and figuring out what are the voltage or the current. In synthesis, it's like, well, given a voltage or current, what is the resistance needed to get that voltage or current? Okay, and a big method that we're going to use is sum of products, and it's going to be sum, which is an or, and products, which is an and. And after we run through a bunch of examples, we'll see how useful this this idea, sum of products, and synthesis of logic is. All right, so let's begin. So I want to build off the last example that we talked about, and that's this kind of interesting interconnection. And so if you recall, these are edge-triggered flip-flops, and you have this little caret here, and this caret is the clock, and that caret means it's looking for the rising edge. All right. Notice this weird interconnection where the input data is connected to the inverse of the output. Here's the output Q, and here's the inverse of the output Q bar. And again, just to review, just an edge-triggered flip-flop by itself. If the clock rises, Q becomes whatever the data pin was, right? So that was the understanding of just this basic edge-triggered flip-flop. This goes bink, this data gets pushed over. Okay, so in this weird interconnection, what we saw here was when this clock rises, because of this interconnection from here to Q bar and also from here to the next clock, you got this doubling of the period from this output to this output. From clock to here, this had double the period of this one, and this Q1 had double the period of this one, okay? And just a plot of that was shown here. Okay, so what we have here is, here's that clock signal. That's this initial clock signal. And you can see that D0 is this guy, and Q0 is this guy. And notice the period of the clock here initially is half of this period here, and the period of Q1, which is that signal there, is double this one. So you get this doubling of the period. All right. Now, an interesting application is actually counting in binary. So if you remember counting in binary, let's say 4 bits 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Well, if we can inspect the rows, columns, every column is going to be double the period of the previous one, just like in here. So what if we took this same idea, we have 2, and I wanted to make a 4-bit binary counter, right? We could make any number of bits, but let's say a 4-bit. I could just cascade 2 more of these with that same interesting interconnection, and I would have, again, doubling of that period, so on and so forth. Okay, so let's look at an example where you have doubling. Okay, and so this is the same exact interconnection as this guy, just added 2 more, right? I have the initial clock, and I have Q0 bar going to its initial data and the next clock, and then same with here and same with here. All right, and what I can do is I can track what is Q0, Q1, Q2, and Q3 doing every time this clock pulses. And because we know that we get double the period of the previous flip-flop, what we would expect to see is something like this. If we were to track Q0, 1, 2, 3, this is Q0, 1, 2, 3, where Q0 is the least significant bit, okay, what we should see is something that looks like this, right? And look at the period, 0, 1, 0, 1. But then Q1, this guy has double the period, 0, 0, 1, 1, 0, 0, 1, 1, so on and so forth. And then Q2 will have double the period of this one, and then so on and so forth, right? And this should match your intuition for how we count in binary, right? Okay, so why don't we move over to a simulation and then see what does that look like when it's performing live. So I'm going to go to share screen, and I'm going to look at my binary counter. Okay, and you all should see this. So this is a 4-bit binary counter. This is the same exact thing where I have the clock here, and this clock is going to be pulsing. I haven't turned it on yet, and I'm tracking Q0, 1, 2, 3, and notice Q0 is my least significant bit. So what I want to see when I start running this is I want to see the binary sequence occur at this output. Okay, so let's run this guy. Okay, 1, good, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, so on and so forth. And so you can see that this is following the whole doubling of the period for every cascaded flip-flop. And if you look at the plot here, you can also note that you're seeing that same pattern. If this is the least significant bit, this is Q0, Q1, Q2, Q3, you see 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, yep, so on and so forth, okay? So all these lectures will be posted to Brightspace, so that way you can play with these circuits if you wish. Okay, so why don't we move back and let's start a new topic called sum of products. And this 4-bit binary counter will actually come back throughout this lecture. I'm going to use it just to drive a truth table so that you can see these truth tables active. Okay, so let's go back. I'm going to stop sharing. Okay, so we're back here at the doc cam. Okay, so like I said in the outline, when we look at synthesis of logic circuits, that's the opposite of analysis. In analysis, what we usually have is given a circuit, we're going to find the output. Well, in synthesis, it's going to say given an output, find the circuit, right? That's kind of the idea of synthesis, right? So given a desired output, we want to create or synthesize the circuit. Okay, so that's what we're going to do. We're going to start with a desired output, which is a truth table. Right? So that's the desired output. And we are actually going to figure out what is the logic gates that are going to be needed to create that truth table, right? And we've done the reverse, right? We've been given kind of complicated logic gates and we built the truth table. Well, we get to do another way. Okay, so there's two main methods. There's sum of products, and then there's product of sums. Okay, and so what we're going to focus on in this lecture is the sum of products. And just another review, sum, remember, means or, and products means and gates. And we're going to look at these things called min terms, right? And these min terms are going to be corresponding to a row in the truth table where you get an output of 1. Okay, there is the dual, just like voltage and current, right? There's sum of products, product of sums. We're not going to worry about this one, but I just wanted to let you know that it exists, right? It's a little more confusing for this one. There's max terms. It's when the rows equal 0, but we're going to ignore this. This is, I think, much more intuitive. And I hope you see why after we do a bunch of examples, okay? Both methods are going to be equivalent, but we will use the SOP. Okay, so I think the easiest way to learn this is just to start with an example. So let's say we have an example where we have 3 inputs or 3 bits, okay? And we're going to give us an arbitrary but desired output. And so if we run through a 3 input or 3-bit system, we should have 8 unique rows, 2 to the 3, right? 0 through 7. Good. And so this is going to be just the binary sequence for 3 inputs or 8 unique combinations, right? 0, 0, 0, 0, 0, 1, so on and so forth. Okay, so this is just a random desired output. Okay, 1, 1, 1, 1 here. Okay, so we're going to use this SOP method to synthesize the circuit for this. So we want to build a bunch of logic gates in such a way that if I were to give any of these combinations of input, I would get that desired output. So let's look at the rules, and then we'll apply our rules to this specific truth table and see if we can come up with a circuit. So what are the rules first? So if we observe, let's put this side by side, row 0, row 2, row 6 and 7, so 0, 2, 6, and 7, they all correspond to an output of 1. Okay. These are going to be essentially our min terms. So lowercase m of that row is going to correspond to these 1 outputs. Okay? And what we're going to do is we're going to take the product of input or inverses for d equals 1. Okay? So product of the input or inverses. let's see what that means. And when we do this example, it'll become very clear. Okay, let's look at row 0. In row 0, I have 0, 0, 0 for the input. Well, what I'm going to do is I'm going to say the min term of row 0 equals, because I have a 0 here, A bar times B bar times C bar. Okay. Now, if I go to this one, row 2, so the min term of 2, this is also 1, so we're going to have a min term for row 2. It should be A bar B C bar. Okay, let's double check. Yep. A bar B C bar. A bar B C bar. Good. Okay, let's try to predict what we're going to see for the 6th row here. What do you guys imagine? A B C bar. Yep, A, B, C bar. Not too bad. And if we go to row 7, it should just be A, B, C, right? A, B, C. Okay, great. Well, what's the usefulness of this, right? And we'll go into that. But let's just clarify what we just did. If the input is 1, we'll just write the letter. And you can see that here, A and B, right? So let's say row 6 again. Input was 1. If we see a 0, then we put the bar, right? So I just summarized that here, okay? And what we're gonna do is we're gonna take all these min terms and add them. Notice these are multiplier products. So what kind of gates are we gonna use? We're probably gonna use AND gates. And if we wanna add the min terms, we're gonna use OR gates. But this is the logic expression for that. So the output D is going to be the sum, look at this, sum of products. You guys follow? Sum of products. And all I did was took A bar, B bar, C bar here, A bar, B, C bar here, A, B, C bar here, and A, B, C here, and added them, okay? There's another way to write it. You could say it's the sum of these min terms M0, 2, 6, and 7. That's equivalent. You could use another shorthand method. You could use the summation, right? The summation symbol, M of 0, 2, 6, 7, right? No problem. These are all equivalent ways, right? And the Greek letter sigma is summation, right? Okay, so I think you have a handle on what's going on here. I'm going to take this expression and I'm going to rewrite it right here. Okay, so we have that expression. I'm going to rewrite here, same thing. Okay, and this is the really easy way of implementing this circuit. Let's just check out how we implement this circuit. Remember, these are AND gates, and this is an OR gate. So what I'm going to do is I'm going to take one big OR gate with 4 inputs, and I'm going to put it right here. So this is going to sum up all those 4 min terms. Now, here I'm going to have 4 AND gates, and they're going to be 3 input AND gates. And so they're going to be right here. Okay, so these are your products. And notice it's following sum of products. No problem, sum of products. Okay, how many inputs do I have? I have 3, A, B, and C. And not only do I need the A, B, C not inverted, I need the inverse. So here's A, B, C, and I have some inverters. And now all I have to do is for every AND gate, so this AND gate is going to correspond to this min term, I'm going to connect A bar, B bar, and C bar to this one. So let's look at how that works. A bar, B bar, C bar. Perfect. Okay, let's do the next one. I should get A bar, B, C bar. So I want this A bar, B, so notice it's on this side, B and C bar. So let's do that. A bar, good. B, excellent. And then C bar. That's this one. Okay, let's do the next one. It should get A, B, C bar. So that's A here, B here, and C bar over here. Good. A, B, C bar. Fantastic. And then the last one, it's all the non-inverted, A, B, C. So A, B, C. Neat. So what I should see in this is that I would get the same truth table output. So this is the synthesized circuit for this desired truth table, right? Remember, synthesis is given an output that's desired, what's the circuit? So we've synthesized using this sum of products method. Kind of neat, all right? So let's look at, well, let's review in our heads what we got going on. We got 1, 1, 1, and 1 here, right? What I have in the simulation is I took my binary counter and I actually hooked it up to here. I have a 3-bit binary counter. I've hooked it up to these ABC. So I want to see this output drive in that same consistent way. And I implemented the circuit for everyone. Okay, so let's go back or let's go to the share screen. I'm going to go back to here. And here it is. So you can see this is the same expression, A bar, B bar, C bar, plus A bar, B, C bar, plus A, B, C bar, plus A, B, C. Here's all my AND gates and OR gates, right? And notice I have a 3-bit binary counter cycling through. And look, the least significant bit is going to C. Okay, that's good. And then the so on and so forth. All right. So I'm going to run this. And so the very first 0, 0, 0, we should actually see high. Good. Okay, so high, good. Should see low, good. Then high again, good. And then I should see 3 lows in a row. Low, yep. Yep. And then I should see 2 highs, good. Good. And so that follows the same truth table desired output as what we saw on paper. Okay, but this synthesized this expression. Kind of neat. Okay, let's go back to do another example. Okay, so we're back here. Okay, let's look at this kind of more crazy example. We're going to have 4 inputs, and we have a desired output. Okay, with 4 inputs, we should have 16 combinations, 0 through 15, and this is the binary sequence, right? Okay, no problem, right? We've done this many times in class. Notice 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, all zeros, all ones, 4 in a row, and then 8 in a row, 0, 1's good. And let's say this is just an arbitrary desired output, right? 0, 1, 1, 0, 1. I mean, it's just a random assortment, right? It could represent something. The last example will actually have a more meaningful example. This is just arbitrary. Okay, and what we want to do again is use our sum of products method to come up with a circuit that represents this truth table. Okay, so again, we look at when the output is 1 and we want to create the minterms, and the minterms in this case are going to be row 1, 2, 4, 8, 10, 11, 13, 14, 15. Let's do it again. 1, 2, 4, 8, 10, 11, 13, 14, 15. Good. These are your minterms, and we have 4 inputs, okay? So let's write down what that minterm is for row 1. Well, what do we have? A, B, C, D, and I think this should be bar, A bar, B bar, C bar, D. Okay, let's check our first one. Good. A bar, B bar, C bar, D. Fantastic. Okay, let's go to the next one. A bar, B bar, C, D bar. A bar, B bar, C, D bar. Good. Let's go to the next one. A bar, B, C bar, D bar. Good. Okay, the next one. A, B bar, C bar, D bar. Excellent. Okay, what's the next one here? A, B bar, C, D bar. Good. That's this one here. Okay, the next one is A, B bar, C, D. Yep. And then what do we have? We have A, B, C bar, D. A, B, C bar, D, good. And then we have A, B, C, D bar. And the last one should just be A, B, C, D. Good. So this is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 AND gates and 1 big OR to bring them all together. Okay. So let's go to the next page. So the next page, we're going to have again ABC. Those are the 4 inputs. We're going to have our inverters. we're going to have the super big OR gate with all the 9 inputs, and we're going to have 9 AND gates here, okay? And we can build this whole thing. So A bar, B bar, C bar, D. Let's double check. A bar, good. B bar, C bar, D. Excellent. And so I wrote down the min terms or the products right here above the AND gate. Just made it easier for me to do all the connections. I can go to the next one. A bar, B bar, C, D bar, A bar, B bar, C, D bar, and that should have been the second one here, A bar, B bar, C, D bar, right? These two correspond, and so forth. And you guys can follow, you know, and do this whole thing, right? All I did was took these one for one and punched them in, and then just made the connections. Okay, it's not too bad. It is a little bit messy, but this does synthesize this truth table, and so this actually implements. Now there are methods to minimize these, right? I'm not going over that in this lecture. There are methods to find out, hey, is there redundancies? Do we have to have all these terms? Definitely. But for right now, I just want to show you kind of the brute force sum of products that allows you to just synthesize these desired truth tables. Okay, so I did again implement this in the circuit sim, and let's see what that looks like. Okay, so let's go to share screen. Okay, and so here is that insanity. Notice there's the 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 products here. This is the expression, right? And then this is the OR gate. Now I put my 4-bit counter in here. Again, this is the least significant bit going to the D, and then so on and so forth, okay? And so what we should see is when we see A bar, B bar, C bar, D, that should correspond to a 0, 0, 0, 1. So when we see a 0, 0, 0, 1, we should see this light up. All 4 of these light up, and we should see this green, and that should enable this, right? When we see an A bar, a 0, 0, 1, 0, we should also see this light up, right? So each time one of these pings, this AND gate or the corresponding AND gate lights up, and we should see a 1 at the output. So let's check that out. Perfect. 0, 0, 1, 0, good. 0. So the next one should be 0, 1, 0, 0, good. Okay, and you can see that this is cycling through. You can see which ones light up, and you can see this green lights up. There we go. And the very last one should light up. Good, perfect. And it starts over. Okay. So these just correspond to every single row that has a 1, right? It's a very brute force, straightforward process, this sum of products. Okay. And what we should be able to follow through here on the truth table is this, I made this as the output. This is E. And this is row D, C, B, A. So if you looked at this sideways, you should see the same truth table laid out here. Okay. And again, all these circuit simulations will be posted so that you can play with them and confirm yourself. Okay, so let's stop that and let's go back. Okay, so let's go to this last example. So the last example is going to build upon our sum of products, but it's going to give a little bit of a meaningful system first. And so the hardest part about this example is just building the desired truth table. Once we have the desired truth table, I think it's now pretty straightforward to do the sum of products process and come up with a circuit. So this is going to be an ignition power example. And so imagine a system. It has ignition, it has gears, it has fumes, it has emergency override, and has a blower fan. And so there's going to be states where you can turn on the ignition, and there's going to be states where you don't want to turn on the ignition, all right? Okay, so the ignition is going to be the output, whether you should be okay to turn on or turn off, right? Now, we're going to have the inputs B, E, F, G. Okay, B, E, F, G. B, E, F, G are going to stand for fumes, gear, emergency override, and blower fan. Okay, so the rules in this example are uh, the fumes, if it's present, if F equals 1, then I has to be 0. You can't turn on your system. Okay, I equals 0. Okay. Now for gear, if the gear is in play, you also don't want to turn on the system. Okay, but there's an exception. If the emergency override is 1, then you can turn on the ignition even if the gear is in play. Okay. Now the emergency override, it overrides G and it overrides the inverse of the blower fan. Okay. And so that means for the blower fan, you must have B equals 1 for I equals 1 unless E equals 1. Okay. So they're kind of related here. So the hardest thing is going to be building the truth table. So we want to create the truth table first, then the SOP for I, and then we'll draw the circuit. But this is going to be probably the hardest part of this method. Okay. So we have 4 inputs. 2 to the 4, that should be 16, or 0 to 15, right? 16 inputs are total combinations. And what we want to do is figure out, well, based on these rules, what is the I that's going to be needed? So let's write down at least our truth table. So B, E, F, G, these are just the 16 binary combinations. All right, good. Okay, so let's build this out. So when the fume is 1, I is 0. So that means you're always going to have I 0 for this case, this case, this case, and this case, no matter what, right? So there's no emergency override here. Okay. Then, and let's see. I think I can write that down actually. So I'll put 0. So I is going to be 0, 0, 0, 0, 0, 0, 0, 0. Okay. All right. Let's look at what else is here. Okay. What else is going to kill our ignition? If the gear is 1 and the E is 1, it looks like I also has to be 0. So if the gear is 1 and the E is 0, sorry, I think that's also a 0. So gear is 1. Good. All right, let's look at this one. Gear, oh, that's already taken care of. What about here? Oh, so this one might be okay. All right, so we'll put that as a question. Okay. And actually, if we go here, this might be okay because the B is, even though the B is 0, we have the emergency override 1 because the emergency override overrides bad conditions for both these two. So I believe that's a 1. Okay. Now let's go to the next one. Gear is 1. That's bad, right? And the emergency override is low, so this has to be a 0. And we go to here. The gear is 1. The emergency override is 1. Okay. And this is 1. Okay, I think this is good right here. Good. Okay, so notice how we've knocked out a lot of these. We only have 1, 2, 3, 4 to deal with. Okay. What about this one? Okay, is this one good or bad? Emergency override is low, gear is low. That's a good thing, right? But the blower is low, and we must have the blower to be 1 for I equals 1 unless the emergency overrides. So this is a 0. Okay, let's look at the next one here. The next one, the emergency override is 1. We have a bad condition for the gear and a good condition for the gear, but a bad condition for the blower, but that's okay. So this should be 1. Okay. Now let's look at this one. The gear is good. The blower is good. The fumes are good. Even though the emergency override, this is a 1. Okay. And then we're here at the last one here. Fumes are good. Gear is good. Blower is good. And emergency, this is all good. 1. Okay, so this is the conditions in which we can ignite our system. And let's double check if that's the correct truth table. Yay, we got it correct. Okay, so now that we have this desired output, now can we synthesize the circuit? And I think you guys know how to do this now. We're going to look at all the midterms, which are the rows corresponding to 1. So that's 4, 5, 8, 12, and 13 in this case. And what do we got here? It's going to be B bar, E, F bar, G bar. B bar, E, F bar, G. B, E bar, F bar, G bar, B, E, F bar, G bar, B, E, F bar, G. Okay. And we can look at, I have it written down on the next page. Okay, good. 4, 5, 8, 12, 13. 4, 5, 8, 12, 13. Good. And these are the corresponding inputs with their inversion or not inversion. Okay. Okay, again, we have how many products? 1, 2, 3, 4, 5. So we should have one big OR gate and 5 AND gates. Good. And I've just one for one written down these combinations here, just so when I make the connections, it's easy. And here's the connections, right? And we'll look at one just to confirm. B bar, E, normal E, F bar, and G bar, perfect. And the rest you can follow along on your own, right? Not too bad. Okay, let's look at the circuit in the circuit simulation and see if we get the same results. So let's go to share screen. Okay, and then we're gonna go to the last one here. Okay, so we look here, we have the 5 products, right? And we should, the first time this should occur is when we get 0, 1, 0, 0, right? This is 0, 1, 0, 1, okay? And so let's run this and see, do we get a ping on the 0, 1, 0, 0? So run here. So when this is 0, 1, 0, 0. Okay, we gotta wait for it. There we go, yep, sure enough. And this is, yep. So you can see it run through. This is again my 4-bit binary counter. And again, if you look at this output here, the scope, this I is this first row, and then this is G, F, E, B. So this is like the desired truth table, but put down sideways. And notice you have row 4, row 5, row 8, row 12, and 13 all here. And I want, this is a little bit of a tangent. I want you to note, look at this little blip. And this is kind of going back to that gray code and that encoder lecture. Notice how you get this little blip because there's a race condition going on. Remember when we looked at the encoder? There's a little bit of discrepancy. One's going a little earlier or later, and so you're accidentally firing off a 1 here, and that just hits home the idea of gray code. But for all intents and purposes, we can ignore that for here, but you can see the benefits of encoder. But to summarize this whole process, we came up with this expression, this logic expression, which built out our desired truth table from all the rules. And then we used this brute force sum of products method to build this out. And all this guy is doing over here is just counting through our truth table so that we can see that, yes, we are getting the desired output. Okay, that's all I got. And thank you for listening. Like and subscribe. And I'll see you on the flip side.